Alright, so the next thing I want to kind of go through is a little bit about the integral test. And what we're kind of sort of basing this on is the thought that an infinite series is a sum of an infinite number of terms, and an integral is a limit of a sum as the number of terms goes to infinity. So there's some definite similarities there in the ideas of an infinite series and a limit. And basically, here's the thing. If we have some series where we can think of a sub k as a function of k for integer values of k, then there's going to be a connection. Well, back up for a second. You got to be careful. If our function f is continuous, which isn't all that big a deal. Most of the functions that we're going to be looking at will be continuous. And our function f is positive, and our function f is decreasing. And that's the one that trips me up, I'll be honest with you. I forget to look for that. So if our function f is continuous, positive, and decreasing, then the sum, if k starts at 1 and goes to infinity, of a sub k, and the integral that starts at 1 and goes to infinity of f of x, are either going to both converge or both diverge. So because we know how to work with improper integrals, and we are going to be able to tell if our integral is going to converge, means we get a finite value, or diverge, going to be infinite, then we can conclude the same about the series. Now, it is important to note that the value that the integral converges to is not necessarily the same value that the series has. Okay? But if the integral is going to converge, then the series will converge. So let's look at some examples. If we have the series from 1 to infinity, come on, infinity, there we go, of the function 1 over the third root of k plus 10. Okay, we would be considering the function f of x is equal to 1 over the third root of x plus 10. Now that function f of x is continuous, it's decreasing, and it's positive on the interval from 1 to infinity. You can check those three things out very quickly by looking at a graph of f of x. The other thing that you could do is you can evaluate the derivative for function f. Sometimes it's hard to tell, even looking at a calculator graph, if our function's increasing or decreasing or constant, if it's doing one of those things very slowly. So if you differentiate this function, we'd end up with negative 1/3 times the quantity x plus 10 to the minus 4/3 power, which is less than 0. So there's evidence that our function actually is decreasing. Okay, so we're considering just the behavior of the function from 1 to infinity. What it does otherwise, we don't really care so much about. All right. Whoops, come back. So we want to take a look at the integral from 1 to infinity for this function, which I'm going to write as x plus 10 to the minus 1/3 power. Well, we know to take the limit as b approaches infinity of the integral from 1 to b. Okay, and I'm going to leave out a couple of those steps. Well, nah, I'll go ahead and do them. Anti-differentiating, we will end up with 3/2 times x plus 10 to the 2/3 power. And that's going to be evaluated from 1 to b. And we'll take a limit as b approaches infinity. So, limit as b approaches infinity of 3/2 b plus 10 to the 2/3 power minus 3/2 times 1 plus 10 to the 2/3 power. Taking a limit as b approaches infinity, we're going to find that this limit is infinite. So the integral diverges. The conclusion then that we can draw is that the series also diverges. Okay, so there's an example where we had an improper integral that goes to infinity. So our conclusion is that the series is going to diverge. Here's another example. Series starts at 2 this time and goes to infinity. The starting point really isn't going to be such a big deal as long as we're kind of close to 1. The same rule is going to apply. Okay, our series is 1 over k times the natural log of k quantities squared. So the function we're concerned with is 1 over x natural log x squared. And we're thinking about this on the interval from 2 to infinity. Now in this case it's important that we're looking at 2 to infinity because this function has a vertical asymptote at x equal 1. So it's good actually that we're looking at 2 to infinity. We have a continuous function from 2 to infinity. It is increasing, it is decreasing and positive. So we're going to consider the definite integral from 2 to infinity of this function. A little u substitution is going to be necessary. If we let u be the natural log of x, then the derivative of u is 1 over x. And I think to simplify my life just a little, you know what? There's just a delay. There we go. All right, 2 to infinity. Wait. Let me go ahead and change that to b. And we're going to consider the limit as b approaches infinity of u to the minus 2 power du. I'm not going to change the limits. Although I could. So since I didn't change limits, I'm going to be careful to remember to rewrite the function in terms of x. So anti-differentiating u to the minus 2 power will end up with minus 1 over u. And that's evaluated from 2 to b. And u is natural log of x, so I'm going to just change that u to the natural log of x. So we're looking at a limit as b approaches infinity of minus 1 over natural log b minus 1 over 2. Now 1 over natural log b is going to go to 0. So we're looking at a limit that has a value of 1/2. So the limit converges. And the series converges. Series does not converge to it does not have a sum of 2 though, or excuse me, 1/2 though. You know what? I left out a natural log. That should be a natural log of 2, and that should be a natural log of 2 right there. Still get a finite value, so the series still converges.